Alright, hey subscribers, welcome back to another episode of Science with Surback. Today what we're going to be talking about is section 16.8, which looks at tying together or relating our Ka to our Kb. So, a couple of objectives that I have for this lesson before we get going. Number one is determine the relationship between the strength of an acid and that of its conjugate base. And then number two, calculate Kb from a knowledge of Ka and vice versa there. Calculate that Ka from the knowledge of Kb. So we start out here with some example equations that we've actually seen before. And what I'm going to do, right here, we have the ammonium ion, which is a weak acid, and that's because it donates its H+. You can see H2O gains that H+, and we form this H3O+, or that hydronium ion. Now, because this is a weak acid, we can write the equilibrium constant expression to be our Ka, and in this case, our Ka is going to be equal to the concentration of our products, which is H3O+, and NH3. So we get H3O times our concentration of NH3. And this is all divided by our aqueous solution of NH4+. So we end up with NH4+. Now, if we go our reverse direction, so this is taking NH3, and it's a weak base, and we combine it with water, what ends up happening is we end up with this equation that we have listed right below here, and because of this, we can write our Kb expression, which is our products, which is OH minus, so OH minus times the concentration of NH4 plus, all divided by our only aqueous solution over here on the left, which is NH3. All right, so now what I'm going to do is I'm going to take my Kb, which I already have written here, and I'm going to multiply it by my Ka. So underneath here, right here, as I am going to take my Kb, and I already have it written, so I'm not going to rewrite it. I'm going to take my Kb, and I'm going to multiply it by my Ka of what I just calculated up here. So what I'm going to do is I'm going to multiply this Kb times my Ka, which is H3O plus times the NH3 times or divided by NH4 plus. Now, if I multiply these together, what happens is this. My NH4 plus, it cancels out because they're diagonal from each other, and so does that NH3. So when I multiply my Ka times my Kb, what I have equal here is my OH minus times that H3O plus. Now, this should look very, very familiar, and I'm going to put a time sign there. This should look very, very familiar because the concentration of OH minus times the concentration of H3O plus is actually just equal to the Kw. And we talked about this early on in our acid-base unit. So our Kw is this, or our general statement that we're going to write down is this. The product of the acid dissociation constant for an acid, Ka, And the base dissociation constant for its conjugate base, Kb, equals the ion product constant for water, Kw. So let me write that down, and then we'll put it in a formula that we'll go through here in just a second. All right, so that written definition is fine and dandy there. But again, I like to see a formula. So this statement, this general statement, could really be summed up by this. Our formula for this, what I just stated up above, is Kw equals Ka times Kb. So what this allows us to do, if we know Ka, we can find Kb and vice versa, because Kw is always 1 times 10 to the negative 14th. It's always that, because that is a neutral substance. So if we go through a couple examples, we can see what happens here. So we have the Ka given for HF of 6.8 times 10 to the negative 4th. Well, we want to find the Kb of this particular scenario. So again, we start out here with our formula. Kw equals Ka times Kb. Now, Kw, from prior experience, is equal to 1 times 10 to the negative 14th equals our Ka, which is given, or you can look it up in the chart if it's not given, and that's in page 1062 of your book. And that is equal to 6.8 times 10 to the negative 4th times our Kb. So to get Kb by itself, what we are going to do is we are going to divide 6.8 times 10 to the negative 4th on each side. So in my calculator, what I'm going to do is this. I am going to end up with 1 times 10 to the negative 14th divided by 6.8 times 10 to the negative 4th. And what I end up getting is this. I end up getting 1.47 times 10 to the negative 11th, and I'm going to round that to 1.5 times 10 to the negative 11th equals our Kb for that fluoride F minus ion. All right, so that's our calculation there. Pretty simple, pretty straightforward. And then we get down here, a very similar equation, except I give you the Kb. We want to know what is the Ka for this ammonium ion. Again, Kb can be looked up in a chart. So again, we start out with that same formula. Kw equals Ka times Kb. So Kw is 1.0 times 10 to the negative 14th equals our Ka, which we don't know, times our Kb, which is 1.85 times 10 to the negative 5th. Now to find Ka, all we need to do is divide both sides by this 1.8 times 10 to the negative 5th. So I'm going to divide each side by 1.8 times 10 to the negative 5th. And so our Ka for our ammonium, if I plug this into my calculator, I get 1.0 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. Press enter, and I get, I'm going to round to 1 decimal here, or 5.6 times 10 to the 5.6 times 10 to the negative 10th is our Ka for the NH4 plus ion. So a pretty simple calculation that ties together Ka and Kb, and it's really helpful because most of the time a problem will only give you Ka. So if it's a weak base problem, we need that Kb. We can now calculate all of that business there. And so our final thing that we're going to talk about here in this video here is this thing called pKa and pKb. So once again, what we're going to start out talking about is this. We start out with our formula. Kw equals our Ka times our Kb. Now, what happens here is this. What if instead of Ka and Kb, because they have those weird decimal numbers, what if we have this? What if we have the negative log of Kw equals the negative log of Ka times the negative log of Kb? So what happens here is this. Instead of just putting negative log of Kw, let's actually insert that value because Kw is not going to change. So we end up with negative log of 1.0 times 10 to the negative 14th equals negative log of Ka times the negative log of Kb. Okay, now if we do this, the negative log of 1.0 times 10 to the negative 14th is going to equal 14. All right, so this gives us a non-decimal number. Now, what we can do here is this. Our negative log of Ka times the negative log of Kb becomes this. These values will become these things called pKa plus our value of pKb. Now, why is this useful? Why is this helpful as this? Well, number one, it puts us in a little bit different scale. It puts us in a little bit more reasonable numbers. And then what we can do is this. We can do a couple of things. Here with our values here. If we have a large Ka, so a couple of statements. If we have a large Ka, one, that means we have a stronger acid. And what that means here is that we are actually going to have a smaller pKa. It makes sense there, right? If we think about pKa in terms of something like pH, right, which is very similar, the smaller the pH, the pKa, the stronger the acid. Now, if we have on the flip side, a small Ka, that means we have a weaker acid. And what this means is we're going to have a larger pKa, which makes sense. If you have a pH, think of that almost as pH. If you have a pH close to 10, that's going to be a base. And that means it's going to be a weaker acid. Now, what we can do here is also counteract that with our large Kb. And so if we have a large Kb, what we are going to have is this. We're going to have a stronger base. And the other thing is, if we have a stronger base, what that means is that we are going to have a larger pKb. And that makes sense. As you increase your pOH, you have a bigger number in that pKb here. Now, a smaller Kb is a couple of things. One, that means we have a weaker base, And then 2, what this means here, it's a general statement, is that we are going to have a smaller pKb, which makes sense as we decrease the amount or the how as the base gets weaker, the smaller that pOH is getting, which means we're leaning more towards an acidic substance. All right, so these are some general statements here. Remember, we can do some calculations. We can do some calculations for our pKa, pKb, but the major thing here is this up top: Kw is equal to Ka times Kb. All right, that's all in section 16.8. Hope you've enjoyed another episode of Science with Surbeck. And as always, don't forget to subscribe.